In this lecture, we will continue our hyperspectral remote sensing topic. So, let us start with the SVM, support vector machine. So, what exactly support vector machine is and how we can use this for our data classification, right? So, SVM optimizes linear separation or classification of data set in feature space. The basis of classification lies in the notion that only the data set lying on the class boundaries are necessary for discrimination, right. So, here we are taking the example of two feature classes, and then in between we can put a hyperplane, or in simple word we can say we are putting a line to segregate these two classes. So, this task is done by the best suited hyperplane that segregates the data set. So, basically hyperplane is nothing but the boundary we are drawing between two different types of data set present in the input data, right. The best suited hyperplane is one with maximum margin. Just imagine a case where you have two classes and in between you can or you will be able to draw a line which can separate these two classes, right. And the best line will be the one with both classes have equal distance or some separation, right. So, that is what I am trying to tell you here. So, the best suited hyperplane is one with maximum margin. Maximization of margin can minimize the problem of misclassification. So, just assume you have this input data set, right. Now, how can you draw a line or how can you segregate this into two classes? So, either by drawing a line here or by line here or by line here. So, in any of these cases you will end up with two different classes. Whether these classes whatever you have identified, whether they are correct or not, that we need to say. That is why we have to use some logic. Accordingly, we will decide where our hyperplane should be, right. So, let us take an example of two feature set randomly distributed in n dimensional space. So, training data set are plotted as this, right, and where I is 1 to k, right, in ND space. Mathematically selecting the optimized hyperplane follows the two conditions. First one is data sets belong to a class should lie to the same side of the hyperplane, right. So, here this is what written. The second case is distance between the closest data set of either class and the hyperplane should be as large as possible, right. Since hyperplane is a line on a 2D represented space, the general equation can be written as this, and this is nothing but the mx plus c, right. So, where x is a point lying on the hyperplane, m is normal to the hyperplane, and mod c by norm m is the perpendicular distance from the hyperplane to the origin, and norm m is the Euclidean norm of m, right. So, I hope this is clear. Now, for linear segregation, the hyperplanes separately defined as this mx plus c, this is the form. Now, here for yi, we have a range from -1 to +1, right. So, this is the class A. In the next class, we have this -1, that is the class for B. So, combining these two equation from this and this, we have arrived at this particular equation, right. The training data point on these two hyperplanes are called as support vectors, and the central line which we were calling hyperplane, right. So, let us see this example here. Assuming we have very two distinct type of classes in the input data, and it is very easy to draw a line here because both are separated with some distance, both means both classes, Now here the margin between these plane is 2 by norm m. So this is what we are trying to draw, and the hyperplane will be in the center, right. So if you see from origin, I have drawn this line, right. So this line is meeting here, and once we have this perpendicular, then the distance will be mod c by norm m, and here this is the distance between hyperplane and these two support vectors. So this is 2 by norm m. So here also you will have the same, and this is the condition for right hand side of this hyperplane, where yi is minus 1 and here yi is plus 1. So the maximization of this margin leads to the following constraint optimization, that is using this one, and this is under the inequality constraint of equation 1, the previous one which we have derived or which we have arrived by using this yi is equal to plus 1 and yi is equal to minus 1. Till now I discussed the ideal condition where both the classes are very far from each other and it is very easy to draw a line, right. But what about in natural condition, and what about your remotely sensed image where you want to derive maybe n number of classes. So n may be 2, 3, 4, 5 or 6 classes or maybe 10 classes. Then how do we distinct or how do we draw this hyperplane? So generally classes are linearly non-separable and thus constraint of equation 1 cannot be satisfied, right. Remember that equation 1. To overcome this problem, new set of variables are introduced which is known as slack variables, which is this one, right. Thus equation 1 get changed to this one where this xi is introduced. Above equation is justified in case of outlier when xi are very large and a penalty term, this one, is added to penalize solution for which xi are very large. So there is very simple method, only thing is you need to understand and you need to change this slightly, or you can mold this method according to your application. So here the constant c, again we are going to introduce this constant c that governs the magnitude of the penalty associated with training samples that does not lie on the appropriate side of the decision boundary. With large value of c, there is a possibility of SVM overfitting, and with a small value of c, an inappropriately large a function of support vector may be derived. With the addition of the penalty term, the optimization problem become this, right. Here the norm m square by 2 tries to maximize margin, where this tries to penalize the cases not located on the appropriate side of the decision boundary. So that's how we are going to improve our method in each of the iteration. If the classes are overlapping in feature space, then this can be too large and the hyperplane may not be generalized well. So let us see what are the advantages we have when we are using this support vector machine, right. So as we know that support vector machine performs very well for two different feature classes. In the classification of remote sensing images, SVM can be used for more than 2 classes, right, because that is the regular practice. We generally want to derive more classes from a remotely sensed images. A very common technique is 1AA technique, right. The 1AA approach is simply division of an n class dataset into n 2 class cases. This example I have put to explain what exactly and how exactly we are performing this support vector machine. So if there are 4 distinct classes, namely A, B, C and D, classification would be affected by classifying class A against non-class A areas or class B against non-class B and so on. So, here basically we start with one class and the rest all are in one class. So, ultimately you will get two classes, then further we introduce the next class and the rest other classes will be considered in one group, right, and so on. We derive this SVM support vector machine hyperplane, and then once the iteration is over, then you will finally get the 4 classes and that is expected to be good. So, till now I have introduced different methods, different procedure how to analyze this hyperspectral remote sensing data. Now, let us see how exactly we are performing this, right. So, I am not going to show you any software related thing, this is only related to the methodology, right. So, the concept you need to understand. So, let us start with this. This is a hyperspectral data captured by Hyperion sensor which is available in this space. Nowadays, it is not in working condition, but this is from the archive data. So, you can see this is only 3 band you are seeing, because for color composite we need at least 3 band, then only you can represent any data, but rest all other bands, all 242 bands are in the background. So, whenever you click on any of the pixel of this image, you will get 242 spectral values, right. So, then you can easily identify what the material is, but exactly how. So, for this data analysis, as we have already discussed, this MNF has to be performed and the inherent data dimensionality need to be identified. Once we are done with that, then we go to PPI, pixel purity index, and then we derive the end member, and once we have the end member, then we use that end member to classify this particular image, right, and once we classify, then you can analyze the result and you can estimate the accuracy of your data. But here we have identified end member from the image itself. So, how do we know what chemical composition or what the material is, right, because that is very important to understand. Then only you can say each pixel of this image which belong to first end member has this chemical composition. Unless until you do not perform a spectral analysis of the end member extracted from the image, you cannot say what is the chemical composition or what material or object is, right. So, for that we need to use a spectral library, that is very important, you cannot avoid this step. So, now here what we are going to do? We are going to use this spectral library spectra which is expected to be pure or which is captured of pure materials, and then you will use the image derived end member together and you will try to match these two, and you will find the best match with the different mixing of the library spectra. So, once you find a particular mix which is matching well with your image derived end member, that means that spectra whatever you have mixed in different proportion, that will give you the chemical composition of the end member extracted from the image. I hope this is clear. I will try to explain one more time so that you should not have any confusion in this. So, basically by performing this and this, ultimately we have got the end member, right, and let us assume this is the end member from this particular image by following this procedure. Once we know this is end member A, let us call it A, then we perform spectral classification like SAM, SVM or any other method you can use here, or SFF, By doing so, you will get a output that will be your classified image. So each pixel will either belong to A, B or C, whatever end member you have provided and which was extracted from the image itself, right, and which was expected to be pure. But pure means what? We don't know what is the chemical composition or what material you are or what pixel you have selected and what is the chemical composition of that pixel. So to know that, we need to use a spectral library. And how do we generate a spectral library? We collect a pure mineral or vegetation or maybe a object, and we collect the spectral signature. We save it in a library, and then when time comes to analyze your end members which was extracted from the image, we use such libraries and we try to match the spectral library spectra and end member derived from the image in different proportion. So here you will mix the spectral library spectra in different proportion and then you try to match with this. Then if you find that 10% of X, 20% of Y and 70% of Z is matching well with your A, that means this particular pixel which is here contains 10% of X, 20% of Y and 70% of Z, right. So that is why we are going to perform the spectral analysis. So this is very, very important. Unless until you don't do this, you cannot show the result whatever you have derived from this image. In addition to that, the quality of the spectral library, that also matters, because the way you have collected the spectra to generate your spectral library, that also plays very critical role here. So now let us understand how do we generate this spectral library and what are the parameters which we need to take care, because once you have a perfect spectral library or a standard spectral library, you can use those spectra to analyze your image. Now here, this is the example of field spectroscopy. You are familiar with this image, right? So here, either we will do this measurement in sunlight or maybe with a lamp, so controlled environment, and then we measure the spectra which is here through this spectroradiometer. So this is just for the example. The instrument photograph is just to show you how this is done in the field and in the lab. This is not to support any company, right? So ultimately we have got this spectral feature which is captured from your spectroradiometer. Now let us see why we exactly involve in spectroscopy. So since Newton's discovery of composite nature of white light in 1664, spectroscopy has been used to study properties of terrestrial and extraterrestrial objects, right? All the organic and inorganic substances exhibit diagnostic spectral feature throughout the electromagnetic spectrum that enables identification of chemical composition and relative abundance of constituents. Diagnostic spectral absorption feature of natural and man-made materials are mainly governed by electronic and vibrational processes, right? With the advent of imaging spectroscopy or hyperspectral remote sensing, by combining the power of spectroscopy and imaging technology, lithological discrimination, mineral potential mapping, and there are many other applications where possible from space and airborne platforms. So this is just to give you a flavor or the background of this particular method, why it is so powerful and how we are using this, right? So hyperspectral remote sensing is extensively used for lithological discrimination and mineral potential mapping. Let's see some critical information which you need to know before you start using this hyperspectral technology. The accuracy of identification and abundance estimation from a hyperspectral remote sensing depends on the quality of spectral library. This is what I highlighted in previous slides, right? Therefore, a well characterized spectral repository of material or object with their physical, chemical and mineralogical details is need to be generated. The reflectance spectra are significantly influenced by several parameters such as instrument calibration, source sensor geometry, roughness of the surface, anisotropy of investigating surface, field of view and spectral analysis technique. So, all these listed parameters plays very critical role in this spectroscopy. Now, let us see one by one why they are so important. When we talk about instrument calibration, this has to be performed before your spectral measurement. I hope you remember the lecture where I have explained the working principle of a spectroradiometer. So, there do you remember that I explained dark current, right, where we used to measure the signal emitted by the instrument itself, right. So, that is why I am mentioning here instrument calibration is very important. Next point is source sensor geometry. So, if you remember my previous lectures, suppose this is how your surface is illuminated. So, here you have sun or maybe a source lamp which is illuminating this particular surface, and this particular direction is used to measure the reflected energy. So, what if we change our position from here to here? The reflected amount will be different because surface is not isotropy. So, that is why we need to take care of the source sensor geometry. In addition, the field of view, because here we are talking about the field spectroscopy. So, here you have a certain field of view which can be used, and then accordingly you fix this H, so it will cover your target. In case if you increase the height, then it will cover more than your object and you will end up analyzing the wrong object, right, or maybe the mixed spectra. So, that is why it is very important to take care of this source sensor geometry. There is one more interesting fact, that satellites are seeing our Earth's surface or maybe any other planet with certain angle, right. So, that angle and the field measured spectra angle has to be same, or the lab spectral measurement has to be same. Then only you can match this field acquired or the lab acquired spectra with the satellite spectra, right. So, otherwise what will happen? You will have different response from the same material because your look angle, source sensor geometry was different. Now, the next point is roughness of the surface. So, here the surface roughness plays very critical role. Why? Because that will introduce the BRDF concept. Now, next is anisotropy of investigating surface. The composition of the material also controls this particular measurement, right. So, if the material is bright, it will emit or it will reflect more. And the next one is field of view. So, I have already explained here. Then spectral analysis technique, what technique, what method you are using to analyze this spectra with respect to library spectra, right. So, these two things are very, very important. A standard protocol of spectral acquisition need to be followed to match the field spectra with the spectra measured from space. Why? Because you need to have the similar mechanism or similar protocol or similar method of the spectral measurement in your lab and as well as in your field. Then only you can upscale this information to satellite scale. This will provide reliability of collected spectra. So once you have followed the standard protocol, then you can match your measured spectra with any other spectra measured elsewhere, right? If both of them are measured using some standard protocol, right? So what advantages we have when we are involved in field spectroscopy? So that's why I have put this question, why field spectroscopy? So it provides you full control of this acquisition process. So you have full control on the instrument, you know whether it is working well or not, what is the weather condition, what is the time when you want to measure, what is the object which you are trying to look, because you can adjust the height and the field of view, right? The second point is known instrument and its sensitivity, whether your instrument is sensitive enough to capture maybe hundreds spectra in 1 second, right? So those informations are available to you when you are involved with field spectroscopy or lab spectroscopy. Source sensor geometry, you have full control. Spectral measurement strategy, how frequently you want to measure, at what time you want to measure, what target you want to measure, everything you can decide. Dynamic field condition can be addressed, because if you see morning 9 o'clock, 12 o'clock and evening 5 o'clock, the illumination conditions are different, weather condition is different. So accordingly you can decide whether you want to collect this spectra, whether you want to have this spectra in this particular condition, yes or no, that is your decision, right? Direct measurement of radiance, downwelling radiance, irradiance and surface reflectance can be done here. In remotely sensed image, if you want to calculate surface reflectance, you need to model this complete atmosphere. But here, since your distance between the target and the sensor is very less, so it is expected that influence is, or the influence of atmosphere is negligible, right? So it also depends what is the weather condition, what is the instrument which is used. So all these parameters plays very critical role, and that advantages we have when we are involved in field spectroscopy. And ultimately we can generate the spectral library. So that is the information required to upscale the lab or field information to satellite scale. There are different spectral libraries available for Earth and planetary exploration, that is from different universities, different organizations which are listed here. I will show you one by one. If you want to access them, you just visit their website and follow the set of instruction. Either you have to enroll, or in other words you have to do the registration and then you can download the data, or else they might have instructed how to get or how to access their data set. So I am just trying to tell you what are the different options available to you when you are involved in Earth and planetary exploration. The first library is from USGS, the United States Geological Survey Spectral Library. The next is JHU, that is John Hopkins University Spectral Library. The third one is the Jet Propulsion Laboratory, that is known as JPL Spectral Library. The next spectral library is Aster Spectral Library, that is a compendium of data from JPL, JHU and USGS library in a standard data format, right? So these you can access by contacting them. Then next is ASU, Arizona State University Library for Planetary Exploration. Then you have EARSL, Emission and Reflectance Spectral Library by the Council of Industrial Research Organization, CSIRO, Australia. And the last one in this list is RELAB. reflectance experiment laboratory. So all these libraries are developed by using different sets of protocol, different instrument, different field of view, different samples. So whenever you are involved in using this one, then you need to take care of the source sensor geometry, sampling rate and spectral spread which have been used while generating this spectral library. Otherwise again you will introduce more error in your analysis. So that's why I have written here. Let us see some of the constraint when we are involved in spectral measurement. So I'll explain you some of the research and then you will get to know what are the different constraints are available or what are the different constraints in hyperspectral remote sensing. So here I want to highlight this grain size, fabric and composition significantly influence reflectance and emission spectra, right. So here you can see there are 7 different patterns which I have used to generate the spectral library, right. So here just to explain this, you just consider when you are having this particular pattern, at particular height I have fixed my sensor, right. So this is your H and this field of view is known. So just to make sure you need to calculate 2 tan theta by 2 and you can focus on your target, right. And by this way I have generated different spectral library of these 7 patterns. So here the total amount of quartz and feldspar was same, only thing is their arrangement was changed, right. So for this purpose we have used a goniometer, and here this goniometer is basically developed and patented by Professor D. Ramakrishnan. He is a professor in Department of Earth Sciences, IIT Bombay. So you can see this attachment. Here you can use to focus your fiber optic cable to your sample. So sample was somewhere here, right, in the center, and here you have flexibility to change or to rotate the position of this particular sensor in this direction as well as in this direction. So you have full control on azimuth and zenith. For more detail about this work, you can refer this paper. By using this goniometer and the previously shown 7 different arrangement of the same quantity of quartz and feldspar, the spectra were measured. Once your sensor is at 0 degree, that means it is nadir looking, that we considered as 0. And when you are moving in this direction and this direction, so you can exactly know where is your 20 degree, right. So by doing or by using this instrument, we have measured the amphibole spectra of 2 to 4 mm grain size from 0 degree, that is nadir looking, then minus 20 degree and plus 20 degree in both sides, right. And here you can see for the same sample, when you are changing the position of measurement, the spectral response is different. But remember here only the depth of the absorption is getting changed. So that means if you have measured the spectra in different angles, you can easily find out what material it is, but when you want to estimate the composition, then it may give you some wrong result, right. In another experiment where we have used quartz 2 to 4 mm and again 0 degree, minus 20 and plus 20, and then we have got this spectra. Again there is a change or there is a shift in the intensity. So only the intensity is changing, right. So independent of grain size, the geometry also affect the depth of absorption feature. That is the result of this experiment. Now if you want to see the effects of grain size and geometry on a spectral shape, just see this spectral response where we have used quartz and the grain size was 2 mm to 4 mm, and here we have 0, 10 degree, 20 degree in both the direction, right. And here you can see in all the cases you have different spectral response, but remember position is not changing, only the intensity is changing, right. With reduction in grain size, the effect of geometry on the absorption depth decreases progressively. However, the shape of a spectral absorption feature was changed when the grain sizes were reduced significantly. The next graph shows the quartz grain, but the size is changed 0.7 to 2 mm, and here also we have 0, 10 and 20, right. So, you can see the result here. In the third case, where the size was less than 63 micrometer. Now, here you see, so does not matter what exactly your grains are, but this explains with reduction in grain size, the effect of geometry on absorption depth decreases progressively. However, the shape of a spectral absorption feature was changed when the grain sizes were reduced significantly, right. Now, what exactly we have done by measuring this information? We have tried to estimate the error introduced by this grains and arrangement, right. So, grains and geometry. So, here the first pattern where we have used 50% of feldspar and 50% of quartz, and then we tried to simulate this and we tried to match this with the measured spectra, and then we found that from the estimated one, quartz is coming 58.1%, feldspar is 42.3%. That means there is a error in abundance estimation. Why so? Because when we are changing the grain sizes and when we are changing the geometry, it has their own effects. Now, in the second pattern also you see it is 55, 45.5, here it is 63. So, you can see here all these values are not close to this. That means you are having significant error in the abundance estimation. You can see here when we are talking about pattern 4. So, pattern 4 is having maximum error, right, RMSE error. If you want to visualize how exactly these errors are coming, so you can see here this is quartz feldspar pattern 5. So, this is for this one, right. Here the blue color is the measured one and red is basically your modeled spectra. So, both are having the RMSE of 4. So, estimated abundances show 3 to 15% error, therefore, these parameters should not be neglected in geological interpretation. So, this is from this paper, but as we know that this grain size and geometry plays very critical role. So, it is not only in geological interpretation, but in any other application the source sensor geometry, grain size. So, these plays very critical role. They play very critical role and they need to be take care while measurement. In this slide, I want to highlight what is the strength of field spectroscopy or hyperspectral remote sensing technique. So, the effect of concentration can be seen here. So, this is the suspended sediment concentration measured in the water and corresponding spectra were measured. So, you see this particular color is showing 500 ppm. That means the water container was having 500 ppm of suspended sediment concentration and then spectra was measured. So, similarly, we have generated for all these different composition, right. This work is published in this particular journal, right. Now you can access this. I have one more figure for you. Here also you can see in different concentration how the suspended sediments are behaving and what is their spectral signature, right? And we have used this particular information to map the suspended sediment concentration in different classes. You can see here the ranges are written, right? So this is just to give you a flavor how or what is the strength of this hyperspectral remote sensing, up to what extent you can use, and what are the limitation or what are the different parameters which you need to take care before the measurement, right? This is another example from coal. So here you can see the coal bearing areas exhibit their own spectral signature, and here we have given all the details of this coal spectra, right? So here you have clay, carbonaceous clay, lignite, how they are different from each other. They are found in the same environment, in the same place, but their spectral signatures are different. So you can use such information to map the way we have mapped the suspended sediment concentration, right? Let's see what are the different potential areas or the potential application of hyperspectral remote sensing data. So the first one is lithological or mineralogical mapping, right? Next one is non-metal exploration, then precious mineral exploration, hydrocarbon deposits. You can also investigate this one. I will cover some of them in application part. Then transportation engineering, you can easily identify which vehicle is parked since maybe 1 week or which is parked just now, what is the road condition. Those information you can derive from this hyperspectral remote sensing. Then crop monitoring, surface deformation, then volcano, whether it is active or inactive, what is the stage of this volcano, right? Then landslide mapping, then planetary exploration and quality control and grade assessment. So some of these application may not require the data directly from this hyperspectral remote sensing, but one of the parameters which plays very critical role in that application can be derived from this hyperspectral remote sensing, right? Now let us see how we evolve over the time. So first, for planetary exploration, we started with telescope, then Hubble Space Telescope, then flyby mission, then orbiter mission, then landers and rovers, then manned missions. So this is how we are evolving ourselves. So it is necessary to update ourselves to know the latest techniques and use them in your application, right? Let's see how this hyperspectral remote sensing data are used in lunar exploration, right? So by several planetary scientists, the moon is considered as an end member among the planetary bodies of our solar system. Several space missions have been launched for expanding our knowledge and understanding about lunar topography and composition. Present day moon mineralogy explain the evidences of past geological history of the moon, right? And here in this particular example, we will be using this moon mineralogy mapper data, that is commonly known as M-cube, and this is one of the example. This is M-cube hypercube, right? And this is for this particular area which is known as Naunobo. Here I have used this M-cube data of global mode, where I had this 85 spectral bands and the spatial resolution was 140 meter, spectral resolution was 20 or 40 nanometer, right? That was the spectral resolution. And this work is also published, you can refer that for more detail. When we talk about the remotely sensed image and especially for lunar exploration, we need to derive this dn number to radians, radians to reflectance. So how we exactly do that? So here there is a new term called I by f, that is the apparent reflectance. So that is calculated using this particular equation, right, where I by f is apparent reflectance, L rad lambda is radiance value measured by m cube sensor as a function of wavelength, d is distance from the sun to the moon in astronomical unit, f sun lambda is exoatmospheric solar spectral irradiance as a function of lambda, theta is solar zenith angle, and p is phase function correction, that is unavailable for this particular data, right. But for some of the data sets it is available. So whenever it is available, you are supposed to use that. This is the exoatmospheric solar spectral irradiances, which is available in these two links, right. And once you use this solar exoatmospheric irradiance and that I by f formula, you can see how this spectra is changing from radiance to reflectance, right. You can see here the trend has completely changed. Now if you remember, I always say that 0.4 to 2.5 micrometer is reflective domain and 3 to 16 micrometer is thermal domain. But what is happening in between 2.5 to 3? This is also allowed by our atmosphere. So we can measure this particular energy. But why we are not using very frequently? Because it has effects of both reflectance and emission. So it is very difficult to separate these two information and derive some meaningful information. So here in this case, I have modeled the black body and calculated the I by f, that is the apparent reflectance, and you can see from 2100 onwards you can see there is an increase. But when we are talking about black body, there will be no reflectance, right, because everything is emitted. But though we are having this particular data that indicate this particular wavelength region is not free from thermal emission, right. So from black body reflectance, it is evident that beyond 2 micrometer wavelength range, reflectance spectra are mixed of both reflectance and thermal emission. Thus the pixel spectra of m cube data may exhibit an increased signal in longer wavelength, right. So how do we remove this particular information from our m cube pixel spectra? Because m cube is also giving you data till 2500 nanometer, right. So in this study, different locations were selected in the m cube image as a test site, namely T1, T2, T3, so on T6, to estimate the temperature of the lunar surface using black body's multi-temperature data, and subsequently thermal component of apparent reflectance were removed. You can see these locations were selected for this estimation, right. Once you have that information, you can see location A at 396 Kelvin, location B at 400 Kelvin. This is A dash and B dash. So what is exactly happening here? For A and B, right, these two temperature data sets are matching. So that means that pixel value or the pixel temperature was here in this range. For location T2, again this is 409 Kelvin, here 430 and 28, here you have 419 and 423. So that is how you can derive the information about the temperature, and you can correct those temperature in your reflectance spectra measured or identified using this m cube data. So in this case, I have followed this particular methodology where thermal corrected apparent reflectance image was used as input. Then dimensionality reduction was performed using ICA, that is independent component analysis. This is the advanced version of PCA MNF, right. The identified inherent dimensionality of M cube image was used to extract the end members, and then we have matched with the library spectra, and here we have performed the classification, and finally we arrived at the result. So, here for this we have used PPI, and here for classification we have used SAM. So, image derived end members were something like this, and here I am calling them with some name, right. How so? Because these are the image derived end members. How can I say this is pigeonite or anthracite or norite pigeonite? So, basically here we have matched with the library spectrum. This is the moment when you need your library spectra to resolve your end members in different composition, right. So, here we have used this linear mixing model. So, a fully constrained linear mixing model was used to identify the minerals and their abundances. So, here is the equation 1. This iterative least square approach resolves each of the M cube end members for constitutive mineralogy based on least root mean square error, that is equation 2, that is the RMSE, right. So, now you can see how best fit we got after this linear mixing model. So, here the modeled spectra pigeonite basalt, right, pyroxenite modeled spectra. So, how these two are matching? So, once you do that, then you will end up with the end members classified in different rock type, mineral, vegetation or object, right. So, then you can easily write these names. That is why I have mentioned this in the previous slide. Once you have this information, you can use this end member to classify your image. Remember SAM, spectral angle mapper, where we estimate the theta between your reference spectra, in this case that will be your end member, and the pixel spectra, right. So, then we measure this theta, where Ti is the target spectrum, Ri is the reference spectrum, I is the number of input spectral band, theta is the angle between target and reference spectrum, and that is how we have got this particular output, where you can see all these colors basically represent different types of rock, right. So, this is how remote sensing is evolving, and now we are able to identify the chemical composition of the material in those pixels from space, right. So, that is all for today. Thank you.